Hi, Calculus. It's Mrs. Jurosik here. I am going to introduce Chapter 3 to you, and I'd like everybody, if you haven't already, pause and go ahead and print out your notes for Section 3.1 if you need to, and go ahead and get your calculators too, because a little bit of calculator work will be needed, and you can pause in addition because I was going to have all of you do the warm-up question with the hole punched out of the W, sorry about that, in first few minutes. So pause and actually try 1A, B, and C for yourself before I actually start talking now, okay? All right, so I'm going to go ahead and get started. So Chapter 3, you officially are now going to talk about derivatives. So derivatives are a rate of change, just like we had been discussing in 3.1, okay? But there's obviously a lot more to it, and we spend half the year talking about derivatives. So the other half of the year talking about antiderivatives. So here we go. If you did the warm-up, okay, I'm going to kind of go through this. It says sketch and find. So if we sketch an x squared graph, right, we want to find the average rate of change from 1 to 3 for each of the functions. So at 1, we're at 1, right? So that's 1, 1 would be one of those points. And if we went all the way to 3, we'd be at obviously 9. So let me do that. Let me fix my picture a little bit. So still not probably best or to scale, but okay. All right, so at 3, we're at 9. 9, 1, 1. So we have the points we need to actually calculate a rate of change. So 9 minus 1 over 3 minus 1 is 8 over 2, which is 4. And what you're quickly going to find is that if I keep sketching, I'm just up 1 unit. So at 1, I'm at 2, and at 3, I would be at 10. So that would mean 10 minus 2, 3 minus 1, 8 over 2, 4. And if I made this like a little bit up here. And then if I try the plus 4, it's the same thing again, just up 4. So our coordinate would be 1, 5, and then we'd have 3, 13. So we'd be at 13 minus 5, 3 minus 1, still 8 over 2, which is 4. What do you notice? They all have the same slope. Have the same average rate of change, so AROC. Okay. Should make sense, because if I were to actually make, and if I take out the calculator, it would look a lot better. But if I were to actually draw my secant lines between these 2 points, obviously human error, it's not going to look exactly the same. But if you indulge me for a minute, if I draw x squared, I draw x squared plus 1, and I draw x squared plus 4. There's x squared. There is x squared plus 1. There's x squared plus 4. If we were to actually draw each of those secant lines, it's the same exact parabola, just vertically shifted. So the secant lines in each case would be lines with the same slope. Okay. All right, the next one. Find the instantaneous rate of change. Okay, well, at x equals 1 for each of the following using the limit definition below. Okay, so a limit definition implies that there is some sort of limit notation to what we're doing. Now, instantaneous rate of change and a limit definition. Well, this right here is simply a slope formula, right here. So as b is approaching 1, okay, that is what we are evaluating, okay? So with x squared, if b is approaching 1, how does that translate? How would that translate? Well, our b value is now our x value. So f evaluated at b. So that would mean instead of x squared in my slope formula, I'd have b squared. And then f evaluated at 1, well, when I plug 1 into my function, I get 1. So so we know we plugged in, right? So b squared minus 1 squared over b minus 1. All right, so if I'm trying to plug in 1, I actually can't do that. Like any other limit problem, I can't plug this in because I'm going to get 0 over 0. So I am going to do some algebra. And that algebra would be factoring. So what I'm going to show really quick is I'm going to write this up here in a simplified version, if you will, right? That's what that is. So I'm going to factor it. And then there's that factor of b minus 1. It would be a whole, right? That we are able to cancel. And now I can plug in 1. 1 plus 1 is 2. So final answer is 2. So let's pause here and see if you can do the same thing with b and c. Okay, and we'll see what we get. Okay, so pause your video and come back. We're back. And I'm going to go ahead and repeat what I just did. So if f of x is defined as x squared plus 1, I'm still using my limit definition that's right here. Maybe I'll start this one up here. When I plug in f evaluated at b, that would mean b squared plus 1 minus f evaluated at 1. So that would be 1 squared plus 1 over b minus 1. So what I have is, I'm going to simplify, b squared plus 1 minus 2. 1 plus 1, 2, over b minus 1. So I'm actually going to end up you're going to notice, you noticed if you paused and actually did the problem, you are in the same exact place where you were in part A. And we're going to simplify, and we are going to get an answer of 2 again. This will still factor, right, into b minus 1, b plus 1 divided by b minus 1. You can cancel, and then we can plug in, okay? And probably not too surprising, but when we did C, we're going to get the same answer. Instantaneous rate of change is the same as we approach 1 on all 3 of these different quadratics, vertically shifted, okay? And I'm going to go back to the picture in just a second that I brought up on the calculator to talk about that a little bit. But let's just plug this in. I know sometimes our function notation with these problems can get a little bit challenging, right? So f at b would be b squared plus 4 minus, now if I plug in 1 squared plus 4 is 5, right? Over b minus 1. So what ends up happening, again, if I simplify the numerator, minus 5 minus 1 is the same thing, except not when you write it wrong. Okay. Okay. So I end up again with 2. I'm going to do b minus 1, b plus 1 divided by b minus 1, and you are at the same answer. Okay. So what is that saying? What this is saying is, instead of asking for an average rate of change, it's not a secant line. What we just did was we want instantaneous rate of change. This is implying a tangent line at 1. Okay, so what's the big difference? So if I just hand draw, if you will, my regular old parabola at 1, 1, right, my x squared 1. That means my tangent line, get my post-it note here, my trusty, I have a protractor here somewhere, I just don't know where. I'm going to try and make an accurate enough tangent line, if you will, for myself, so that it's touching, right? Just touching at 1. What we are saying is, what is your instantaneous rate of change? What is that tangent line's slope at 1? Okay, well, it says from the limit definition as we approach 1, it's 2. Now, does it make sense that if we only change the parabola's vertical placement on the y-axis, that it's going to stay the same? Yes, because obviously hand-drawn, I won't be able to replicate it exactly. But if I draw my one that's shifted up 1, that tangent line should not change slope. Same thing with adding 4. Tangent line slope should not change. They are identical. They're just in different places on the y-axis. Okay, all right. Starting to get the feel for what derivatives are. Okay, instantaneous rates of change. For f of x equals 3x squared, find the instantaneous rate of change at x equals 2 using the limit definition. So here's what I'm going to charge you with. I'm going to tell you what the answer is right now. I want you to pause, and I want you to do this one. You should get 12. You should get 12. And when we say limit definition, use the same one as this, except your setup is going to be slightly different, because this set at x equals 1, and notice what you have, f at 1, b minus 1, b approaching 1. So what do you think you have to do for this problem? Change your definition slightly. Have to change the definition. Okay, so then if we're doing 3x squared, that would mean when I plug in b, where x is, 3b squared, minus, and then 3 times 2 squared over b minus 2. So 3b squared, 4 times 3 minus 12 over b minus 2. So if I factor out 3, still not able to plug in 2. Still not able to plug in 2. But 3, b plus 2, b minus 2, b minus 2 on the bottom. There is our factor that's causing an issue. Now I can plug in 3 times 4 is 12. Okay. So I'm going to say now, if you have, I kind of made this because I wanted the notes to be limited to a certain amount of space. We're going to have a little bit of difficulty fitting all of this in this space. So you can either continue down here, depending on how you like to work your notes, or if you're working in your notebook, great. I'm just going to grab a little bit of scratch paper for myself so that I don't have to cram it all, so you can see what I'm doing for this next problem, okay? Okay. Now find the IRC. IRC is instantaneous rate of change. A little bit of shorthand, okay? That's me on the end. Okay. Here's another version of the limit definition. So I keep referring to something called the limit definition. So a limit definition is simply a slope formula, a take on the slope formula. So now you're going to bear with me for 1 second. And guess what I'm going to draw? I'm going to draw what kind of resembles, and it's not exact, an e to the x graph. I'm going to say that's x. This right here is, if you will, x plus some amount. We're going to say that that some amount distance between x and this is h. Okay, x with h added to it. Up here, what is my y value here? This is f of x. What would this one be? F of x plus h. Those are my y values. Hopefully, if I were to tell you right now, we're going to find the slope of the secant line connecting those two, you can kind of see our limit definition developing. So my slope, if you will, would be f of x plus h, y2, minus y1, minus f of x, over x plus h minus x. F of x plus h minus f of x over h. If we add limit notation to this, let's add limit notation to it. Looking like I crossed it out. Didn't mean to do that. If we add limit notation to that, we are specifically saying where h approaches 0. So we're going to combine a bunch of ideas right now. Let's think about this. I called this the instantaneous rate of change. Previously, I had said instantaneous rate of change lends itself to tangent lines. It does. So if we're finding the instantaneous rate of change using our limit definition, well, this is a secant line I just drew. However, we take h and we approach a distance. Remember, h is this distance between these 2 points. If we approach a distance of 0, basically nothing, what we're doing is we're bringing this in and this in so close together, there is no distance, and h is basically nothing. So that brings us to a place on this graph which would be equivalent if I drew a tangent line right there. Because remember, your distance is nothing. Your distance is basically nothing. It's forcing the instantaneous rate of change. So you're still using a slope formula, but you are so close together, you're calculating its instantaneous rate of change and not an average rate of change. Okay? All right, so what I'd like to do is take this problem all the way through using the limit definition. So this is problem 4. Okay, and I'm going to move that. So when we go to plug in limit, h approaches 0. So we need x plus h plugged in where x is. Okay, that means where x is in the function, right there, I plug in x plus h minus f of x. Well, that is simply the function itself as written over h. All right. I cannot put in 0 for h right now because I get 0 over 0. I have to do some math. I'm going to do some distributing. 3 times x plus h squared. We've done this in class before. You have to FOIL. You have to distribute. Okay. My limit notation follows me as I do the problem. I haven't changed anything except the form that it's in. So I'm distributing 3x squared plus 6xh plus 3h squared minus 3x squared over h. Okay. And now I still can't plug in h being a 0. But I can do 2 at once here, do 2 steps at once. That's what now allows me plus 0, right? I'm plugging in 0. So I got to 6x, but remember, we're looking for the instantaneous rate of change at x equals 2. So that means that gives me my expression for the instantaneous rate of change. Now I'm taking that expression and I get to plug in an x value of 2. And guess what I get? I get the same thing that I got in problem 3 when I used this specific version of the limit definition. This is still a slope formula, but what differs about this formula as opposed to your standard or your traditional limit definition of a derivative, instantaneous rate of change, derivative, instantaneous rate of change, okay? What's interchangeable is the fact that here you're actually plugging in that x value you're approaching into the function itself. On this traditional one, we actually just place the function with the x's in it into the form and work with the actual expression, okay? You will see a lot of this in the months to come before your AP test, and you will see a bit of it on the AP test. Probably traditional format of the AP test, a couple of questions at minimum on something limit definition related, okay? All right. So I guess what I want to do before we actually try the following question, because we're gonna actually do the next question. If we compare 3 and 4, maybe I'll do it this way. If we compare 3 and 4 with each other, okay? What we did in this question and then what we just did, ending up with 12 in both cases, we were finding the instantaneous rate of change as we approached 2. 2 was plugged in already. The 2 stands out. The 2 stands out. In this form, we were calculating in the end the same thing, except we first simplify it to an expression that still had an x, and then we plugged in the 2, okay? Both got us to the same place. Both are forms of the limit definition. So if we look at question, I'll say 4a, because I don't have it labeled. Like, let's think of that as 4a. Just interpret the meaning of this question. Combine 3 and 4. Okay, you see that h in there from this, right? I also see a 2 plugged in. I also see a 3 as a coefficient. So what this problem is doing is it's taking two ideas in one, and actually it's a shorthand. Shorthand. So if you want to pause and think about it yourself and try and write something down, and then unpause to see what the answer was, take that time. So I'm not looking for an answer, numerical answer. I am just simply looking for what does all this notation mean? And what this notation means is this is the instantaneous rate of change. And when I say that, right, IRC, you could also say derivative of, what function are we dealing with? F of x equals, the coefficient is 3. The 2 is plugged in for the x. So 3 root x, so we're taking the instantaneous rate of change of 3 root x at an x value of 2. And the bottom line is, AP questions revolve around interpretation more than anything else. You won't have to be calculating all of this on your problems. You don't have to do this every time. What you have to do is recognize that this notation means this. You are asked to find a derivative, an instantaneous rate of change, at a particular x value. Okay, so I don't want to read, but I'm going to read. In the last chapter, we used the limit to find the slope of a tangent line. Without knowing it, you were finding a derivative all along. A derivative of a function is one of two main concepts from calculus, the other being integral, which will be addressed later. The first task is to introduce the fundamental concept of the derivative, which is a function derived from f. Suppose a function f represents a quantity of interest, say the variable cost of manufacturing an item or the population of a country. The derivative of f is another function, f prime. So we will, in these two sections, 3.1 and 3.2, start getting into notation. We've seen that on a couple of documents too, where I've said, you don't really have to worry about that now. This is another way of notating a derivative. F with a prime or an apostrophe mark on it, which gives the changing slope of the curve y equals f of x. Equivalently, the derivative of f gives the instantaneous rate of change of f with respect to the independent variable. Independent variable being x, always, right? Time or x. We use limits not only to define the derivative, but also to develop efficient rules for finding derivatives. The applications of derivatives are endless because almost everything around us is in a state of change, and derivatives describe change. Okay. All right. So the next page of notes brings us to notation. Okay. So I'm not going to be, this isn't going to take much longer, but we are going to need our calculators, and I want to just go over some notation pieces. We just saw this. This was the official. It simplifies to just h on the bottom, remember? Right? Simplifies to just h. So that's our limit definition, traditional form of limit definition. Alternate form. There are many alternate forms, and you need to be comfortable when you see basically any of them. You don't have to memorize them, but you have to, when you see this limit as x approaches a, something that looks like this, that is the alternate or an alternate form of limit definition. This one is traditional. Okay. All right. The instantaneous rate of change at x equals some value. Okay. So this one is at x equals some value. There's something plugged in. Okay. This you don't see as much. You can see it. M with tan subscripted would be a slope for a tangent line specifically. Again, not real popular. You see it sometimes, not often. All right. F of x minus f of a, x minus a on the bottom, as we approach a, when we're finding the limit. Could be equivalent to the slope of the tangent line. In words, slope of tangent. In words, instantaneous rate of change. All interchangeable expressions, words, phrases, all the same. Other notations, now mathematical notations. Y prime, right? Y prime equals, same thing as saying f prime at a. So this would be a derivative at that value a. Same thing as saying, ooh, we've seen this. We used the calculator once, remember? We saw that dy dx, change in y over change in x, delta y over delta x. Referring to derivative, so referring to an instantaneous rate of change. D dx of f, not as popular. So I'm going to put pink around the ones that are popular. The ones that you don't see as often, I will leave blank. So not as often. Not as often. df dx. Change in your function f over change in x. D dx of y. Very unpopular. Just putting the y out to the side. Very, very, very popular. We'll put an asterisk by this. Probably the most common form of what you're going to see. Okay. All notations meaning the same thing. All right. So the next, to close out this video, we're going to find the equation of the tangent line to 3 root x, recognize that, at x equals 2 using 3 methods, without the calculator. Okay, so here we go. Without the calculator, this one would mean we need to use conjugates. So I'm going to do this pretty quickly. Pause for yourself, but I think this is worth the time and effort, because if we plug in 0 for h immediately, we're going to get 0 over 0. You have to do something else. Conjugate review is always good. Again, don't get caught up in, oh my gosh, so complicated. And what did I say? I keep saying conjugate, and I'm just not. There we go. There we go. Conjugate. When you multiply the top out, it'd be 9 times 2 plus h. Remember, this negative will cancel with this positive, and then leaving us with these two being multiplied. Negative 3 root 2 times positive 3 root 2 is negative 9 times 2, which is 18, minus 18. Let me just write all of my other goodies. So this is 18 plus 9h minus 18, or h times 3 root 2 plus h plus 3 root 2. 18, negative 18. 9h. There it is. Waiting for all this time to be able to cancel out those h's. H, H. There we go. You could also take a 3 out from the bottom and then keep simplifying, but I think I'm going to leave it for right now and just see if I can plug in my h safely and go that route. Okay? I didn't factor it out, so that should be in the parentheses. All right, so I'm plugging in 0. If I plug in 0, I have 9 over 3 root 2 plus 3 root 2. 9 over 6 root 2. You can leave your answer. You can also simplify. 3 over 2 root 2. Okay. And just for the sake of what we're going to do next, I'm going to do this. 3 divided by 2 root 2. Oh, I should have actually cleaned that up. This is the correct answer, but I got kind of sloppy there, right? I shouldn't have. Yeah, I guess that's okay, right? Yeah, that's okay. 1.0606 or 0.061. Okay, as an approximation. Okay. We're going to use dy dx as a refresher in the calculator to get slope. So that would mean in the calculator to use dy dx, I actually need to put it into my y equals. So that means I need to put in 3 root x, 3 square root x. Graph it. And then dy dx is second trace choice 6. And I have to tell the calculator at what value. It's at 2. Right? We're at x equals 2. dy dx, instantaneous rate of change, is 1.06066. So let me write out the steps. Graph y equals 3 root x, or I should say in y1, because you do need it. Graph. Is graph okay? Graph is okay. It needs to be in y1. Second, trace, and then second trace, it's in number 6. dy dx, and then enter x equals 2. Okay, so for some steps to use the calculator to use your dy dx function. Okay. There's another function in the calculator, and I apologize on my copy. I will have edited and posted them correctly. This should be on the next page, so my apologies. At least I think it should be. Oh, no, I just should move this down a little bit. So sorry, it's so close. We are just finding our method 3 is doing the same exact problem with a function in the calculator again. Here's a new one. There's a new function in the calculator. And it says using the math function. So we have a math button on the calculator. If you scroll down the math function, all right, now we know the word derivative. We're going to use our choice 8 and deriv. So for those of you with newer calculators, newer operating systems, this should pop up. We need to tell it ddx, so it's with respect to x that we're taking the derivative, the instantaneous rate of change. Here we have to put in the function. Notice, I have the function in y1, so I've been talking about this in my class a lot this year. I can just go do this, or you can retype 3 root x. And at the x value of 2 is what we're looking for. Instantaneous rate of change on 3 root x at x equals 2. So I'm going to second enter. I'm going to do this again. And in here, that's what I was going to clear out. So I could do 3. You could always just put it in there if it's not in your y1, right? Same thing. It's not in y1. There you go. So with the math function, math, that was number 8, I believe. Choice 8. And you want to do d dx, function, and then x equals, so this would be our 3 root x, or in y1, and x equals 2 there, okay? All right. All right. We're going to skip over this. You can do that in your free time, or if you know already the answer without doing much, yay, but we'll talk about that one in class. And then maybe I think maybe we'll do this in class as well to make the video a little bit shorter. And by the way, I do love math. Okay, so we'll save this problem also for class, okay? So I'll make this video, cut it off now. It's already been too long, okay? All right, I'll see you all in class. Bye-bye.